Good afternoon, everyone. Let's get started. I want to first, before going into our new topic, just talk a little bit about projects. There isn't anything super new here. I just want to remind you of what you should be doing at this point of time. And I think every week I will remind you of where ideally you would be. So I hope you have chosen an option among the three that were given to you. And I hope if you have chosen to work on an open research problem or reproducibility project, you should be having some kind of idea of the topic, the problem you're working on, or the paper you want to reproduce, and the reasons why you want to work on that problem and on that paper. You might not know all the specifics, that's fine, but if you are claiming now, okay, I decided on a topic for open research problem, and I ask you, okay, what are you working on? You can give me like a high level description of your idea of the problem and your solution, and why do you think that solution is relevant, given what you know about the problem, and why do you think it will work? So you have to have some kind of like high level understanding. In any case, if you haven't done that and you're choosing these options, you should really get close to doing that. And reminder, I have office hours tomorrow. You can come swing by my office at the time of office hours, and you can prepare your spiel. Don't come and just talk and ramble about all the things you have thought about NLP ever. Have some kind of pitch for me, and I can tell you whether that makes sense for me. So definitely use the office hours both with me and TAs to kind of run your idea by one of the core staff. You should be this week working on your literature review for the project. So you should be understanding what other people have done and what is the gap, basically. So a reminder that you are going to work on an empirical problem, most likely, which means that you need to have a good baseline, as always. So don't choose something that's too simple, too old, and then say, well, look at this, I just changed, I use pre-trained model instead of a randomly initialized model, and now I can be better at this super standard benchmark, which wouldn't make for a good project outcome. When you're doing literature review, think about most critical works and themes. There are so many papers in this field, and it's so easy to get easily, lost in the huge amount of papers. So try to just get that one central theme, and you don't need to report every single paper that exists on this topic, although, comprehensive literature review is certainly important. And yeah, identifying gap, that's important. And this might be a little bit hard for you if you haven't, been in NLP around like for a long time. You might, don't worry too much if you don't get too stressed. Is this really a gap, or am I thinking it's a gap, but it's not really? And as I mentioned before, you can always ask me, hey, I think there is this opportunity to do this project, because I don't think anyone has really explored this question. Do you know whether, someone actually has done this? Feel free to ask us that. In terms of instructions, I just added if you're an undergraduate student and you're working on exploration of data artifacts, we have given you a link to a starter code, and we tested it, so it should be working fine. And I also given you instruction to CHPC. CHPC is our cluster at the University of Utah that has GPUs. And this is a great way to run experiments which are a little bit more GPU intensive. There is a slight learning curve to CHPC, but I think the instructions are pretty straightforward. It is a little bit scary to run to put a job in a queue for the first time. And you need to use a queuing, which is managed by a system called Slurm. If you're ever gonna, continue working in this line of work, you are gonna run all of your experiments on servers. Like idea of running your experiments on your local laptop is not something we ever do. And if you are dealing with any kind of server where other people can use it as well, and there are GPUs, you are going to use Slurm. So this is a good opportunity to also kind of learn a little bit about these queuing systems, and it's definitely going to be helpful for you if you plan to, use to work in NLP in the future. Both TAs and I have run experiments on CHPC, so if you have any questions around that, you can ask us. There are some questions we might not answer, and there you need to reach out to CHPC's help desk, which is they're very fast, and I always got good help from them. So definitely reach out also to them. And then even if you manage to run your jobs and you get some, they are kind of looking like they are running, very often we run into CUDA memory issues. This is something we cannot solve for you. This is something you need to kind of try to fix by playing around with the batch sizes. I remember there is that gradient accumulation, which is a nice way to simulate larger batch size. So if you can't fit, for example, you want to use batch size of 16, but you get CUDA memory issues, instead you can use batch size of 2 and a gradient accumulation of 8, and that simulates 2 times 8 equals 16. That simulates the batch size of 16. So you can play around with these things. There is a little bit of, it's a little bit finicky to get used to it in the beginning, but then I'm sure you can all, circumvent CUDA memory issues eventually. All right, any questions about the projects? Okay, just to get the sense, how many of you plan to work on an open research problem? 1. On reproducibility? About 7. And on data artifacts? 1, 2, 3, 4, 5. Okay, good. We have a pretty good mix between reproducibility and artifacts, less on open research problem, which makes sense. And I think if you don't have a great idea for an open problem immediately, working on reproducibility is definitely a better choice, which might turn into an open problem once you start. If you reproduce the baseline and then you have all these new questions, it turns into an open problem. All righty, so last week, we talked about examples of sequence labeling, and those were 2 tasks, part of speech tagging and named entity recognition. And although we didn't really motivate these tasks to think about as language as a sequence of part of speech tag or a sequence of named entities, to some extent, we talked a little bit about, especially when we talked about part of speech, we talked about this as a sequence of potential grammatical roles that makes sense. And now we're going to start moving from thinking about language as this, sequential object into thinking about language as a tree object. Which brings us to syntax. Syntax is the set of principles under which sequences of words are judged to be grammatically acceptable by fluent speakers. And we have already learned one of the most basic syntactic concepts, and that's the syntactic role of each word. How did we call this? Sorry, can you repeat? Yeah, exactly. So the part of speech tag is the most basic syntactic concept we have introduced, which tells us syntactic role of a word in a given sentence. However, syntax here says it's a set of principles. So there are more than one principle, more than just a grammatical role of each word. And when we talk about syntax, people will often talk about how we arrange words and phrases together to form meaningful grammatical sentences. And this is actually where word syntax originate from. It originate from a Greek word that talks about arrangement. So sometimes you will also see a definition just says syntax is the study of how to arrange words and phrases. Syntactic parsing is the task of assigning a syntactic structure to a sequence of text. And here I kind of emphasize syntactic structure because this is pretty vague. I didn't tell you exactly what the syntactic structure is. And there is a reason behind this. Just a small digression. into what is a grammar informally. Grammar is a broader term that encompasses all implicit rules by which speakers intuitively judge which strings are well formed and what they mean. And this includes syntax, whether the words are put together in a proper order. It also includes morphology, which we know now is how we change, inflect the words, which wasn't super important, slightly important for English, but more important for other languages like Hungarian and Turkish, as we learned last time. Also sounds, how we pronounce things, to some extent semantics, and sometimes pragmatics, how we use the language. So that's informally what's grammar, and not to be confused with grammar formalisms. Grammar formalisms provide a set of mathematical rules or algorithms that can be used to generate the syntactic structures of a language. Just going back to being vague about syntactic structure, different theories of grammar propose different formalisms for describing the syntactic structure of a sentence. And the two that are most important for computational reasons are constituency grammars and dependency grammars. Today, we are going to talk about constituency parse trees, and on Wednesday, we are going to talk about dependency parse trees. So just to kind of recap this part, syntactic parsing is the task of assigning a syntactic structure to a sentence. And depending on what theory of grammar we decide to embrace, we are going to get different formalism for what this specific syntactic structure is going to be. And today, we are going to embrace the constituency grammar, and we are going to describe the formalism for parsing with constituency grammars. Why should we care about constituency parsing? Constituency parsing can help models to get the right interpretations of words. So, for example, we have this sentence, and we can read it in two different ways. Visiting relatives, visiting being adjective of relatives, can be annoying. They visit you and take your time and space. Or visiting relatives coming to their space can be annoying because you would rather do something else. Hopefully not the case, though. Hopefully you like your relatives. I don't know why I came up with this example. Maybe something. Yeah, we want to go into therapy here. Okay. So there are, like, depending on how we understand the relationship between words, we can have different interpretations of these words. And of course, it can help models who need to computationally process these sentences. It's also a getaway to think about recognizing who is doing what to whom, which is important for doing a task of, for example, semantic role labeling, where you, given a text, you say, this is a person who is doing the action, this is the action, and this is the, the object of that action. So, for example, here, the cat chased the dog, the verb is chased, and by knowing that the cat is the subject of this verb, we can then understand that the cat is chasing the dog and not the other way around. These are very simple examples, of course, to you. You immediately know the meaning, but for models to understand this, they do need to explicitly or implicitly model these kinds of relationships. Syntactic parsing is a helpful feature for downstream tasks, such as machine translation. For example, you might want to translate from a language which is predominantly subject, verb, object organized, such as English, to language which is verb, subject, object organized, such as Welsh. And you have here, I gave you a link to which languages are SVO, which are VSCO, to kind of see that there is a lot of them that span different groups. So if you know what is syntactically subject, verb, object, and if you know this rule that in this other language, well, you shouldn't be arranging words as a subject, verb, object, rather verb, subject, object, then by knowing what is a subject, what is a verb, what's an object, you can do this proper arrangement. Parsing is also useful for grammar checking. Sentences that cannot be parsed may have grammatical errors, or at least be hard to read. And, today, you might be wondering, well, we have learned neural machine translation, so I know I don't need to take care of these rules. Remember, there is lots of languages, we don't model them all. So for some languages, we still might not opt for a neural approach. But also today, you might want to chunk your text into phrases. That might be useful for all sorts of analysis of text. And for that, you're always going to use constituency parsing. So there is plenty of reason why we should care about parsing. All right, so as I said, today we are going to embrace a specific formalism and try to parse sentences within that grammar form. So I said we are going to talk about the formalism we are kind of embracing is constituency grammars. And the type of parsing is the constituency parsing, which is a method that breaks sentences down in its constituent parts. Constituents are words or groups of words that function as a single unit within a hierarchical structure. So here we have constituency parsing 3. It starts with the start symbol, which is going to be sentence. And here we have so-called noun phrase, NP. And here we have a verb phrase, or VP. Knowing these terms is also useful beyond just constituency parsing. In NLP, people will say noun phrase or verb phrase very often, regardless about whether we are talking of parsing or not. So here, for example, the building is a single noun phrase, and that makes a constituency. These are two words that together function as a unit, specifically a noun phrase. Or here we have a verb phrase, and this is a constituent that is formed by run to the building. So these words altogether form a functional of a unit, namely verb phrase. The goal of constituency parsing is to break down sentences into constituents, but then the way we represent it is using a parse tree. What you can notice is that this is not a binary tree, because here, for example, we don't have two branches, we have only a single one. And for English, it's going to be right branching, just as a consequence of how English language works. And it's important to know that constituency, syntactic constituency, this idea that arranging words that come one after the together make this functional unit, does not hold for every single language. If a language is more free, such as Latin or Russian, then this constituency parsing is limited. And hence dependency parsing, which we're going to talk about on Wednesday. So just to know that the idea of constituency is not perfect. And that's why we have these different theories and different ways of parsing. Okay, so we have learned that, okay, there is a sentence. We can find some constituents, namely words or phrases that function together as a unit, as a meaningful unit. And we found all of them. It makes sense to put them together in this hierarchy, which is for us going to be a tree. So how hard is this? We learned, for example, that part of speech tagging wasn't so terribly hard, right? I won't give you here numbers, but I want to show you that it can be hard. Namely, there is this concept of structural ambiguity, that the grammar can assign more than one parse to a sentence. And we are going to go over a few different examples of ambiguity. So first one is going to be PP attachment ambiguity, where PP refers to the prepositional phrases such as here, to the building, okay? Something with attached to the word. So we have this example. The children ate the cake with a spoon. Can you give me a normal reading of this sentence? And can you raise a hand just because it's going to be too overlapping if we all speak at the same time? Yes, please.
The children use the spoon to eat the cake.
Great. What's the other reading of this sentence?
Children eat a cake that has spoon.
Yeah. Unfortunately, hopefully that unfortunately didn't happen. But that is a valid second reading. And actually, it would be a legit reading if we had, instead of a spoon, icing, right? Totally normal way of reading it. So depending on how you read this sentence, you might have these two different parses. Here I'm giving you a parse tree in this bracket notation, which is a little bit ugly. But what's important here to notice is that here the noun phrase ends with after the cake. So what the cake, its own unit. But here the noun phrase ends after the spoon. So a unit is the cake with a spoon, all right? Which we don't really want. We want that the second parse when we have icing, because then icing is the part of the cake. All right, question about this. Please stop me if you have any, difficulty understanding these examples. Second example here is plastic cup holder. Can someone tell me a normal reading of this sentence? Yep. Great. Yes, that's one reading. For me, that's not how I read it. So I shouldn't have said normal reading because normal to me. So that's one reading. It can be cup holder and it is a plastic, right? Yeah. So for me, I thought it's more common reading because holder for a plastic cup, like how is it different than, I don't know, ceramic cup? That's why. So you can have this through different reading depending on what is the modifier. So here in this first parse, the plastic is modifying cup holder. That was my reading. And then the other reading is that plastic is modifying the cup. So we have a special holder for plastic cups, which would be different than holders for different kinds of cups. Okay, then I have two more examples. This is the problem of complement structure. So here we have the students complain to the professor that they didn't understand. So that is what we are talking about here. So one way to read this is that students didn't understand, like you don't understand, and then you complain to me, which you don't commonly do. You are very, very kind and don't complain much. But then other reading is that they complain to the professor they even never met, right? Oh, sorry, that's not true. I think I had another example here. Let me just read this once again. Sorry.
It's saying like it could be that like perceived that the professor didn't understand.
Yeah, that's true. That's true. I think I had an initial example which no, and then they didn't know the professor is what I want to say. Sorry, did you raise your hand or?
Yeah, could there be another reading that was like whether you were assigning they to the students or they to another group?
Yeah, that's true. It's a different kind of, that's more like how are we resolving the pronoun they, right? That's the ambiguity there, which is something we are going to talk also next week when we talk about coreference resolution. Okay, and finally, we have the coordination scope. So here, coordination refers to this word and. So the man has both a telescope and a head. Oh my God, I don't know why all of these, I feel like I gave you versions of my examples, which were intermediate. I saw the man, that man with both a telescope and a hat. Luckily, I know them by heart. Okay, so I saw the man with both, with a tel and without both. But I don't know how this came about. So I saw the man with a telescope and a hat, and one reading is that I saw the man that has both the telescope and a hat. Another reading is that I saw a man with a telescope and completely separately I saw a hat. Okay. And here, again, the noun phrase, the constituent is the man with the telescope and a hat. So I saw like one entity that has both of these things, but here we have two different noun phrases. One noun phrase is the man with a telescope, and the other noun phrase is the head. So these are examples of syntactic ambiguity and why parsing is not as trivial as maybe initially might seem when I showed you very short examples. The longer the sentences, it becomes way more complicated, of course. Okay, so today our goal is, given a sentence, find the high scoring parse tree for it. And to do that, we are going to apply something called CKI algorithm to something called probabilistic context-free grammars. And this is a bunch of words you likely haven't heard before. So how are we going to do this today? Is first, we're going to talk about context-free grammars, what they are. Then we are going to extend them to probabilistic context-free grammars. And then we're going to apply that CKI algorithm to these PCFGs, which is abbreviation for probabilistic context-free grammars. And that's going to give us solution to this question, given a sentence, how do we find the high scoring parse tree? Yes, please.
How do we find the score?
We are going to find out at the end of today's lecture. Yeah. So CKI algorithm is going to give the score, but we haven't, first we're going to talk about, we are going from right to left here, basically. Yeah. Okay. So let's first talk about context-free grammars. All right. So, as we define, hidden Markov models and discrete Markov model through a mathematical definition, that's how we are going to define context-free grammars. I have a sense it was sometimes hard to read these mathematical way of introducing something. So if you're kind of unfamiliar with that approach, always read it precisely and exactly as it's written. So here, this definition says that the context-free grammars are tuples of these four objects. So when we think about what are context-free grammars, your head should immediately go into, it is a tuple of these four things, and now we are going to see what those four things are. So be very precise if we are defining things mathematically. It's not a matrix, it's not a sequence, it's a tuple of four objects. All right, let's go over what each one of these are. N is a set of non-terminals. Non-terminal is a new term we are introducing, and this is going to referring to all those constituents we have seen in the parse tree, not words. So S, sentence, noun phrase, verb phrase, PP, and part of speech tag, which are the last, layer before we see words. And therefore, sometimes part of speech tags will be called pre-terminals as well. Just for my simplicity, I'm gonna copy paste this parse tree from here because it's gonna be easier to show some of these things, right? So non-terminals are here: S, MP, VP, PRP, VBZ, PP, and so on. But notice that before we see the actual words, like she ran to the building, we see part of speech of every single word. So here she is a pronoun, ran is a verb, in is a preposition, there is determiner, and building is a noun. So this last, second to last layer are part of speech tags, and therefore we call these pre-terminals. Because the words are what we call terminal symbols. That's where we end the tree. So we have this tuple. It's defined by a set of non-terminals. Sigma is going to be our alphabet or lexicon of terminal symbols, which are words. And R is a set of productions or rules. Each rule will be of the form A to beta, where A is going to be a non-terminal, such as NP, and beta will be a sequence of symbols in a union of our terminals and non-terminals. So either a terminal like a S or NP or a word. Okay, so for example, this is a rule that says that NP can be produced with the proper noun. And here, it's not a sequence, it's just one of them, which is totally allowed. We talked about how these trees are not binary trees. And besides that, we also need a designated start S, which will always be in our constituency parse trees sentence S, because in English, very often we do constituency parsing over sentences, and therefore S as a starting symbol. Okay. So just one more time, this is a mathematical definition. Therefore, if I ask you, what is a CFG, you need to give me a mathematical definition, right? You need to follow the exact words that are said here. So let's now see just one example of how we can realize this definition in a concrete example. So let's say we have a set of non-terminals to be this: a sentence, noun phrase, verb phrase, determiner, noun, or verb. Terminals can be, we said these are going to be our lexicon, so words such as the, a, cat, dog, sleeps, eats. We have these production rules that says, okay, sentence can be realized by noun phrase followed by a verb phrase. Noun phrase can be produced by determinant followed by a noun. A verb can be produced by a verb followed by a noun phrase. This here means or. You can also realize noun phrase by just a verb. Similarly, here we have determinant can be realized either by word the or a. Okay, so this means or. And then we have start symbol to be equal to the non-terminal S, which means sentence. So this is an example of CFG grammar. It's defined by tuple of these four objects, set N, set sigma, set R, and a symbol S. An example of CFG. With this CFG, with this grammar, we can generate simple sentences like the cat sleeps. We can start with the starting symbol S. We can replace S with noun phrase followed by a verb phrase. We can use this rule. We can replace noun phrase with determinant followed by N or, other option. That's the rule that, spells this out. We can replace determinant with the using this rule, replace noun with the cat using this rule, replace weepy with the verb, and verb with sleeps. And this is how you would generate the sentence, the cat sleeps, using this CFG. So this grammar can be seen as a way to produce language, very limited language. Okay, just want to stop here to make sure it's clear. That's, I defined the CFG. This is an example of CFG. Any issues with that? Yeah.
It's always one non-terminal on the left side of the rule.
Yes. So all of them have to have this, according to the definition, all of them have this, this form where A is always a single non-terminal, whereas beta can be a sequence of either non-terminals or terminals. Yeah. We are going to, at some point, also restrict what betas can be when we start talking about CKI algorithms. So beta will also be more restricted than what's written over here. Okay, so just want to emphasize that here we have so-called binary rules when beta is produced from two symbols, unary rules when they are produced by a single when beta is produced by a single symbol. Don't get confused by or here. These are more or less like two separate rules. And this is a symbol for or. Okay, so I said we are going to introduce CFG. Now we are going to introduce probabilistic CFG or PCFG. And then we are going to apply CKI algorithm to PCFG to get a parse tree. So we are building these steps until we get what we want, which is a parse tree. Okay, so probabilistic CFGs informally I'm not introducing you a mathematical definition here, although you can easily derive it. PCFGs are CFGs, so they are still a tuple of N, sigma, R, and S. But each one of the rules have probabilities associated with them. And these probabilities represent the likelihood of a particular production or a rule being used in the derivation of a sentence. We have seen those structural ambiguities. So these kinds of probabilities tell us a little bit about which one of those rules would be more likely. By now, we should know that anytime I mention probability, you know that you can estimate it from data, right? And very often, especially now that we shifted to more statistical NLP, you know that we can estimate probabilities by counting and normalizing, which we are going to do here as well. Let me just see. Yes, on the next slide, I'm going to spell that out, but maybe I can talk about it now. So to estimate probabilities, we can use, as always, a supervised approach. So we need a data that's labeled, meaning we need sentences that come with a human annotated parse trees. These kinds of data will be called tree banks. And I already mentioned pen tree bank, for example, that comes in Arabic, English, and Chinese. As we did with the hidden Markov model, we didn't actually do mathematical derivations, but we said that we want to maximize the probability of the data. With hidden Markov models, we wanted to maximize the joint probability of sentences together with human annotated sequences of part of speech tags. Here, we want to maximize the likelihood of sentences together with human annotated parse trees. And if we did the derivations, what we would find is that probabilities that maximize the likelihood are can be estimated by counting and normalizing, which means that for each one of the rules, you're going to look at the left-hand side, and you want the all the probabilities of all the rules where we have a certain symbol on the left-hand side, as here, you want them to sum to 1. So you are going to count how many times you see S followed by NP-VP, and then you're going to divide that number by how many times you see a rule where S is on the left-hand side of the rule. So in this example, we have 150 times the non-terminal S was on the left-hand side of the rule, but we have seen this specific rule where it's followed by NP-VP 100 times and where it's followed only by VP 50 times. So the probability of these rules can be estimated by count over all of the counts, which is here 2/3 and here 1/3. And as always, when we are doing counting and normalizing, we add a little bit of smoothing to avoid zero probabilities. So what I said here a little bit, maybe as a, along the way, that the probabilities for all rules expanding the same non-terminal should sum to 1 is important. So here we have, again, some set of rules, and VP had occurred on the left-hand side twice in 2 rules. So probabilities of these 2 rules should sum to 1. And here I just use that they are equally probable, but maybe just for, it's too nice. So I'm going to remove it and say something like this, just to not confuse you and into thinking that they are uniform. Here we have, for example, determiner also occurring twice on the left-hand side of the rule, which means that the probability of these 2 rules should also sum to 1. And same with noun and verb. S and NP occur only once, so therefore these probabilities of the first 2 rules are 1. So that's what I have written here. The sum of the probabilities of a rule for a specific non-terminal occurring on the left-hand side of that rule should sum on to 1. And this should hold for every single non-terminal, okay? And then the probability of the tree is just the product of the probabilities of rule in a derivation of that tree, which is just a probability of product of these conditional probabilities of rules giving the left-hand side of the rule. Okay, so talking about math maybe doesn't work as nice. So let's stop here and see whether that's clear. Is the first equation here that for every non-terminal that occurs on the left-hand side of a rule, such as S, NP, VP, determiner, N or V here, the sum of probabilities of rules where that non-terminal is on the left-hand side should equal to 1. So we have a distribution over the rules for every non-terminal that appears on the left-hand side. Okay, nodding is a good sign. And then here we have a probability of a tree just being the product of the conditional probabilities as always. That's so-so. Okay, so this part will become also clearer with CKA. Yes, please. Yes, so R is a rule because R, capital R, we have defined it as a set of rules. So R is a set of rules, and when we say some R in a set of rules, that means that this is a rule. ST means such that, so we have a special condition. Here, N is any of the non-terminals over here. And I'm using LHS to denote the left-hand side. So it's spelled out here. So you have, each rule has a left-hand side, what appears before the arrow, and the right-hand side, what appears to the right. And here we are saying for a specific N, and all the rules where that non-terminal is on the left-hand side, the probabilities of the such rules should sum to 1. So for example, if N is a VP, then two rules that satisfy these conditions are these two, and we are saying that their probabilities, the sum of probabilities of these two rules should sum to 1. That's what this equation is saying.
I guess small n means terminal.
Yeah, so sorry, not terminal, but non-terminal. Non-terminal, yeah. So I'll write that nicely, but maybe here I'll just add for all n in n. Oop, whatever that was. Okay, hopefully this makes it a little bit clearer. Yeah. Where n was previously defined as a set of non-terminals. All right, so we defined these CFGs as CFGs, extended CFGs, where each rule is extended with the probability. We had, requested that we have a distribution over rules for each one of the non-terminals. So the sum of these probabilities should sum to 1, and the probability of the tree is product of the conditional probabilities of these rules. And we have also mentioned that these probabilities, as always, can be estimated from data by counting and normalizing. This count then normalize doesn't, as I said last time, it's not just because we think that's a good idea. We didn't derive that, but these are estimates that maximize the likelihood of the data, where our data is supervised data. We have sentences together with their parse trees. Okay, So now we learned what CFGs are. We have learned what probabilistic CFGs are, minimal difference between two, and probability of each rule was what was the difference between them. And we have seen how to estimate the probabilities of the rules. And now we are going to use an algorithm that's going to be applied to PCFGs, which will give us the high scoring parse tree for a given sentence. All right. So CKI is a bottom-up parser, which means that it starts by recognizing the smallest components, like individual words, and it gradually builds up the larger structures, like parses or entire sentences. It's also like Viterbi algorithm. It's a dynamic programming algorithm, which means we are going to parse efficiently. And this is achieved by looking at all substrings one by one and analyzing them and storing possible derivations for those substrings, like which kind of rules can give us that substring. And these results are stored as intermediate results. And whenever we see that substring as a part of a larger string, we reuse that information, that result, which told us, yeah, you can produce this string using these sequences or these rules in grammar. And because we're applying it to PCFGs, and PCFGs have these probabilities, it allows multiple entries for each substring in the table. And when it stores these intermediate results, reflecting that there are different ways we can use those rules to get the same string. And then it finds the most likely parse when applied to PCFG. If we are, if we are applying it just to CFGs without probabilistic part, then we will get possible parses, but we wouldn't know which one is the most likely. Okay, I'm going to explain it through an example. But before that, the first step in our CKI is going to be to something scary sounding, to convert the PCFG to Chomsky normal form or CNF. This is also known as binarization. And all this means is that when we have the rules, we have seen A and beta being on the left and the right side of the rule. The Chomsky normal form requires that the right-hand side of every rule or production, so betas should include either two non-terminals, so NPVP, for example, or a single terminal symbol, a single word. So what this says, convert PCFG to Chomsky normal forms is requiring is that all of the rules are such that on the right-hand side, we have our betas have to be either two non-terminals or a single terminal. And in that sense is binarization. I will not show you how to do that, but it's nothing super complicated. You just need to remove all unary rules and transform and array rules. So if you had from one non-terminal, let's say 4 branches, you will need to reshape your tree such that you get 2 branches. And although this might seem initially like, okay, this is quite something now from, betas being a sequence of any kind of sequence of non-terminals. So terminals, we require very, small, like we allow only small number of betas to be on the right-hand side of rules. This turns out to not be a super strong assumption. So that's why CKA requiring this and then applying it, it works. Okay, so that's going to be our first step. Not showing you an example, not requiring you to know how exactly we are going to do this. All I'm requiring you to know is how the right-hand side of the rules should now look, which means either 2 non-terminals or a single terminal. All right, so The second step in CKI is to initialize the so-called parsing table. So it's going to be, depending where you look at how CKI works, you will see different kinds of representations. Here I'm using the table. Sometimes people will take just this part, this upper triangular matrix over here, and they're going to kind of rotate it. So this point is going to be over here. So it's going to look a little bit funky and maybe nice. It's not important. I'm just, maybe if I had, maybe I can show you here. This classroom is very limited. Okay. Let me think whether. Okay, I don't have anything to write on this board. Oh, yeah, great. Yeah. So, yeah, what I'm showing you here, not super important. I just want to, if you are looking at a different textbook and now you see a different kind of visualization to not be super confused, but you could have, okay, I'll try to write huge, which is not something I know to do. It's fish. So here we have like a starting point 0, and then we saw one word, so 1, see second word, then 2, and then we see so the third word, so 3. This is where these numbers are coming from. And then you would have something like this. And basically, kind of want to take my laptop and shift it. Can you imagine taking this triangular matrix and then rotating it like this? So here, okay, it's gonna be 0, 1, 2, 3. So I have too many. Okay. All right, so. Yeah, it's gonna look something like this. Okay, I don't know how to exactly produce this, but it's gonna have this kind of a shape looking. This one. Okay, something like this, which is basically the same thing you're seeing here, just in a tabular form. So this part over here, this thingy is the exact same thing as this thing. It just rotates. And a point I'm trying to make is that maybe sometimes you're gonna see people representing it like that. It should not confuse you too much. I like to work with the table. And I'm not special like that. In Girafsky's and Martin book, you're also going to see a table instead of this kind of illustration. Okay, so we are just going back to the CKA. Our next step is to create this table, and here pretend as if you have added this dummy column in the beginning, because what you need to do is start counting columns from 1. And the reason is because each one of these cells represents a span of words from I to J word. So here, for example, a span from the first to the third word means I just want to make sure I'm not telling the wrong thing. So from 0 to 3 is she eats fish. Then from 1 to 3 is eats fish. Okay, so it's I guess the way to read it is you are starting at word 1 which, we are starting to count them from 0, 1, 3, 2, and then 3 is where you finish. I think this is kind of nice to think about that. So let me, okay, over here. So let's say 0, she, 1, eats. I was scared for a moment. I was like, there is no 3. Okay. Alrighty, so this can help. So here when we look 1, 2, 3, we are looking at which words span are in between these numbers. So in between 1 and 3 are eats and fish. What's in between 0 and 3? She eats fish. In between 2 and 3, just a fish. So this is how to map these indices into which words correspond to these indices. So yeah, sorry about that. It's a little bit confusing. All right, so we created a cell, we created a table. Each row in each column corresponds to a word in our sentence, but we are starting to count columns from 1 and rows from 0. So the way I like to think about that is if I have added this, dummy column over here. The way to kind of connect these cells to actual words and phrases is to put these numbers in between the words starting from 0, and then you can read each one of these cells is which words appear in between these two numbers. So 1 and 2 each appears between these two numbers. Okay. What CKI is going to do is going to populate this table such that we store the most probable non-terminals that can generate the corresponding substring of the sentence. So we are going to start populating these cells. These are not the values of the cells. Here, I just wanted to show you the indices of these cells. Okay. So we are going to populate the parsing table. First thing we are going to do when populating this table is we are going to fill in the diagonal of the matrix with the non-terminals that can produce that word along with the probability of that production. So here, NP, we see that we can create NP with she with NP, and the probability is that is 0.5. We can create fish with an NP probability 0.5. And eats with the verb with the probability of 1. Notably, if we had if we were able to create she with another non-terminal, we would also populate it over here. Okay, but when later on we would look at the maximum, like if we are. Anyway, I will not make that point right now. Ignore me. Okay, so that's the first step of populating the table is fill in the diagonal. Now, we are going to, here I'm giving you a bunch of words to give you just an overall procedure, but then we are going to go over cell by cell to see how to actually use this procedure. Important thing, because this is a bottom-up approach, we are going to go column by column, left from right, bottom up. So from bottom to the top of the cell. So maybe you can tell me then, just to make sure that's clear, which here, let's use numbers, which we have populated the diagonal. What is the next cell we are gonna populate? Give me the indices of that cell. If you are starting left to right, bottom to top. 0, 2, that's right. So the first column is populated. We move to the next column, and over here, this is populated. So the next one above it is empty, and that's the one we need to populate. And then we would move to this column, start with this cell because it's the bottom cell, and then move up. Okay, so this is our goal to populate this one. Okay, so for every cell that's not on a diagonal, we are going to find the so-called split point, which is any kind of index that occurs between I and J. So, and that corresponds to different possible substrings. So we are going to find the split point of a substring, and then we are going to look for basically, because we are trying to reuse operations we are going to look at, do we have, or we will definitely have information of what had already been, computed for the substring that appears. If we cut a string in two substrings, we will have information about the left and the right substrings. So basically, this is what these rules are saying. You find a split point, then you look into your cells that corresponds to those, substrings that you have now created. And you look for the non-terminals and rules that can produce those substrings. And then you use that information. So it's really hard to now explain it just by, basically reading out loud these steps. So let's see in an example. I think it's going to be much clearer like that, although it's not super easy to work out an example for this algorithm. So here we have a cell 0, 2. What this procedure tells us is to first find all possible case that are in between I and J. I and J here are 0 and 2, so only possible K here is 1, right? So we have K equals 1, and then this tells us, okay, look at these substrings, IK, which is for us 0, 1, and KJ, which is for us 1, 2. And look at the cells with the same indices correspond to those substrings. So here, if you look at 0, 1, which is IK, we are in this cell, which says, okay, here you have an NP. Okay, then we look into another cell, which is KJ, for us 1, 2. And here we see, all right, there is verb here. And then what the next step of this procedure tells us, well, now look for any rule in your CFG where we have B followed by C, which are for us NP followed by V on the right-hand side. So now we are looking for NP followed by V. We have NP, VP, VP, V, NP. Oh, close, but not the right order. V, she, fish, it's. Bummer, there isn't one, right? So here we are gonna say it's gonna be empty, or now I'm just putting the empty set to emphasize that we covered this cell and we didn't find rule in the grammar that that can produce she eats. Okay. Now, as I said, we are going from left to right, bottom to up, which means that the next cell is over here. Okay. Just want to stop for a moment to see whether you are following along. Okay, so left to right, bottom to up. That's how we are covering cells. Each cell has indices I and J. Next step in our procedure is to find the split point, all case in between I and J. Yes, please.
Then, where is the empty 0.5 from?
Sorry, second.
Where is the 0.5 from?
0.5.
Yeah.
Yes. So here you see there is okay, that's something we populated over here. So when we were looking at the diagonal, we are looking as how which non-terminals can produce word she, word eats, and word fish. So basically we are going to our grammar, which we have over here. These are the rules we have in our grammar. That's something we need to set beforehand. No one is giving us that. We need to have rules beforehand. And in this grammar, we see that on the right-hand side, we see all of our words, which has to happen. And we see that she can be produced by NP and with the probability 0.5. This is something we had collected, estimated from the data. I mean, here it's a toy example, so honestly, it's just some random numbers I put here. But in reality, we would have these rules, then we would have a tree bank, and we would count the occurrences of these rules and normalize them by how many times we see a rule with NP on the left side. So that's why these two, they have to sum to 1. Alrighty. Okay, so we came over here. Now we have split point being 2. So we look at okay, so we look at 1, 2, and that brings us to this cell where we have eats being a verb. And then we look at 2, 3, so KJ, which shows this NP. And now we ask ourselves, okay, first thing we found is that we found non-terminals V and NP. And now we ask ourselves whether we can find a rule with V followed by NP on the right-hand side. Do we have such rule in our grammar? We do, right? So here is that rule over here. Bingo, we found it. So what we are going to do in this cell, we are going to store VP, which is the left-hand side of that rule, together with the some probability. Not this one, but something else. I'll show that in a second. So here we have VP, which comes from this rule. And to store the probability, we need to basically do this chain rule. So we have our probability of the rule times the probability of each one of these non-terminals producing corresponding word in that string. Because remember, each one of these cells corresponds to a string, a substring. So here, 1, 2, 3 is, as I said here, whatever occurs between 1 and 3, which is eats fish. So the probability is going to be probability of the rules times probability of non-terminal generating the word times the probability of non-terminal generating the word, which is 0.5 times 1 times 0.5, which is 0.25. And this is what we stored over here. I try to find like how people, what is the formula they exactly use for this, and they don't, I wasn't super successful. So I write you something here where basically in the end when we are looking for the most likely parse tree, here we want to store the non-terminal, which has the maximum probability. So if we had 2 choices here, we would choose the one which has higher probability, and which one of these probabilities you can kind of decompose it in this way, where you have the probability rule together with the probability of each non-terminal producing specific word in a substring. But yeah, take this with a grain of salt and to some extent, because it looks very formal. I just wanted to help you kind of have a formula, but I haven't seen anyone else introducing the formula, which is very strange. Okay, so we have now did our VP, this cell, and the final cell is the one over here. This cell has indices 0 and 3. So now choices for K are not, it's not just a single choice, it's 2 choices, 1 and 2. First, we are going to see what happens if we take the split point to be K equals 1. That means we need to look into IK being 0, 1. So that points to this word she. And we also need to look into KJ, which is going to be 1, 3 over here, which points to this VP. And now we are looking for, these are the non-terminals we found in these cells, NP and VP. And we are thinking, okay, is there a rule with NP followed by a VP on the right-hand side? Is there one? Okay, what is it? I see nodding. Oh, you're so quiet. All right, louder. S followed by NPVP. So the first one, which is 0.9 over here. Okay, so great. I have recorded that. And then if you do the similar kind of probability product, you will get this probability. But don't forget that we had 2Ks, right? So we recorded 1K. And this is important, right? I said that this allows applying CKI to PCFGs allows us to model ambiguity. So here we have actually potentially a second option, and then we will look at which one is more probable. So if we look at K equals 2, then we need to look at the cell IK being 0, 2, which is eats, where we don't have anything, and then at 2 KJ being 2, 3, which points to an NP. So the non-terminals we found is NP. However, we do not have any rules with NP on the right-hand side of the rule, so we don't record anything else over here. So we have populated our table with all the values. And now the question is, where is our parse tree, right? We get our parse tree because, although I wasn't showing that, we were also, all those arrows I was showing, you can imagine if you are implementing this algorithm that you recorded them in a way that enables you to retrieve them back. These are called backpoints. So you use those backpoints to retrieve your parse tree. And although this might look like a funky way to illustrate a parse tree, the green arrows here are actually showing you a parse tree. It's just that you will need to rotate it and, you know, have nicer non-bended arrows to, you know, have a prototypical parse tree. So here we have S pointing to an NP, she. That's what we have here, right? We have S pointing to a VP, great. S also points to VP, right? And VP points to two things, verb, eats, and it also points to NP, noun phrase, fish. And that's actually the parse tree that we wanted, right? Okay, so this example doesn't, I mean, it's already complex, I think, to kind of understand how all these cells, you know, work together. But I really want you to remember that if you had multiple choices that you would record them together with their probabilities, but then if you are looking for the most likely tree, you would use the, for each one of the cells, you would record the non-terminal with higher probability. And then in the end, you get the probability of a tree being whatever you have associated with the start symbol S over here. Okay. That's CKI. That's what gives us the most likely parse tree given that we are applying it to PCFGs. Any question? I mean, let me just emphasize that one point that I'm kind of reiterating. But if we didn't have probabilities here, we would just have these non-terminals, right? And then if we had two choices, we wouldn't know which one to choose. So it would give us CKI applied just to CFGs, would give us possible parse trees without knowing at the end which one is the most likely. Okay, questions about this? Yes, please.
Is it necessary that the most likely parse is the correct parse?
I don't think so. I mean, this whole grammar has limitations. For example, as I mentioned, in the languages with free order, the whole idea might be funky, right? So definitely, I do not expect, although I don't know, you know, I cannot point you to exact result, or I could, you know, later if I do literature review, so let me know if you're interested, but it's my high expectations that this situation might happen. And it also, you know, it's a reflection of the data you have. So if you had very limited data, very small annotated tree bank, of course, your probabilities will not be great, and then the whole thing will be thrown off. Yeah. And when I talk about dependency grammars on Wednesday, we'll see, different way of approaching all of this. Okay, so in the last 5 minutes, I also want to talk about how do we evaluate these things. And similarly, you know, when we had machine translation, you are kind of using the trees you have to determine whether your tree is good. So first of all, you need a supervised data. So you need data labeled with parse tree for evaluation, which is always the case in machine learning, right? So you have a tree bank, and your evaluation basically answers how much the constituents in our hypothesis parse, which is the parse we created with our algorithm, look like the constituents in the hand-labeled reference parse, which is a parse that some human annotator or multiple of them had annotated. And we say that a constituent in a hypothesis parse, so automated parse, is labeled correctly if there is a constituent in the reference parse with the same starting point, same ending point, and the non-terminal symbol. So given that definition of what means that a constituent is correct, you are going to calculate recall and precision, which you need for your F1 score. Your recall will be the number of correct constituents in hypothesis parse, given the total number of constituents in the reference parse. Excuse me, this is going to be recall, like how many of the constituents in the parse tree have you actually correctly retrieved. And precisions will be you know, amongst all of the constituents in your automated hypothesis parse tree, how many of them are correct. And then you combine precision and recall in a standard way to get the F1. I said, and I want to clarify this to not confuse you, I made an analogy with machine translation because you need the label data. And also we don't have this precision and recall are not in the same as when we calculate the F1 score for classification task, where the classification is on the sentence level. You need to have specially designed recall and precision. So in that sense, I made a parallel with machine translation. But this is how you calculate it. And, you know, for a while, these results were not in high 90s. And then with neural approaches, there was a big boost in performance of these models. And we didn't talk about how to approach this in a neural way. But remember, every single one of these tasks I am mentioning, part of speech dynamic recognition or parsing, you can also approach in a neural fashion. Okay, let's stop here. And then please, a reminder, work on your projects. There aren't strict, you know, requests to submit anything to me, but I'm happy to help, and don't let that derail you from working on this early, because the criteria will be such that you had these weeks for working on your projects.